and for giving me a wonderful segue to the next speaker. Since you're talking about observers, our next speaker is one of the world's most accomplished observers in cosmology, I would say. And the introduction will be given by Professor Tamara Davis from the University of Queensland.
Hi, thanks very much, and hi everybody. Good morning, afternoon, evening to everyone. I'm really pleased we can join this conference from around the world, even though I would have loved to be there with you all in person. It is an honor today to be able to introduce Professor Wendy Freedman, who will be giving a talk on the tension in the Hubble constant and whether there's evidence for physics beyond the standard model, something that's interesting in the context of information universe. I've been a fan of Professor Freedman for quite a long time now. She first came to my attention when I was a student back in the 1990s, and she was co-leading the Hubble Space Telescope Key project. The aim there was to measure the expansion rate of the universe, so I think there's really no one better qualified to give a talk on H0 tensions than Wendy. Back then, of course, the H0 tension was worse than it is today, but the uncertainties were also a bit larger. Wendy is originally Canadian. She got her PhD from the University of Toronto in 1984. Then she went and received a Carnegie Fellowship, became faculty a few years later, and by 2003 graduated to being the director of the Carnegie Observatories, a post I believe she held for 11 years, correct? For a long time, Wendy was also chair of the board of the Giant Magellan Telescope. She's won more prizes than I'll try and name here, but they did include things like the Gruber Prize, and she even has a minor planet named after her, I discovered. So I'm really looking forward to this talk. So without any further ado, please take it away, Wendy.
Well, thank you very much for that really kind introduction, Tamara, and thank you to everyone for this conference and the invitation to speak here, and for the opportunity to speak after Charlie Lineweaver. He always gives a thought-provoking talk, and I love the discussion. And I am going to switch gears a little bit and speak as a biological organism to try and interpret the information that's coming to us, what we're learning as cosmologists. And let me try and share my screen here. And I understand it's a broad audience today, so what I will try and do is give some background before I leap into our current measurements, and give you some sense of how we've put together our current standard model of cosmology. And we've learned an enormous amount in the past century about the universe and how it is evolving, and put together as cosmologists what we call the standard model. It's a model that differs an enormous amount from what we would have said a century ago. We would have, as observers, there was no evidence that the universe was expanding, and we thought that the universe's composition was what we see around us, that is ordinary matter. And what we're familiar with, the biology, chemistry, and physics that we are familiar with on Earth today. And what we've learned is that the universe is in fact dynamic. It is expanding, began from an origin of a Big Bang explosion, from which we see the remnants of that radiation today. And it's filled with a substance that the ordinary matter that we're made out of is only about 1/6 of the total matter content of the universe. And the universe appears to be filled with what we've now referred to as dark matter. And even more surprising is that it's filled with a type of substance. There's a tension in the universe that's causing the universe to accelerate in this expansion. And so the discoveries that we made in the last century, the expansion of the universe, the existence of dark matter that interacts via gravity, does not emit light, and the discovery that the universe is not simply expanding, but it is accelerating. Now, of course, probably almost everyone is familiar with the fact that these two individuals, Edwin Hubble and Albert Einstein, Einstein beginning in 1915 with his general theory of relativity that describes the fact that the energy and matter content of the universe determines its geometry or its curvature. And at the time that Einstein came up with the general theory of relativity, he did in fact consult with astronomers of the day, and there were no indications that the universe was anything but static if you observed stars, which astronomers had been doing for centuries. And so he was forced to introduce this term, the cosmological constant, to make the universe static. And in 1929, Edwin Hubble, using the telescopes at Mount Wilson in Pasadena, California, observed stars within nearby galaxies, for example, the Andromeda galaxy, and the particular kind of star called a Cepheid variable, which allows you to measure the distances to galaxies and determine that the universe was in fact expanding, that if you compared the velocities of galaxies as a function of their distance, galaxies that are farther away in distance are moving away from us at faster velocities. And there's this linear relationship that bears his name, the slope of this relation. We now know as the Hubble constant, and this is the Hubble-Lemaitre diagram. And Hubble also was the person responsible for in using these measurements to discover that our universe is filled with galaxies that are similar to the Milky Way. There are about 100 billion such galaxies in our observable universe. And within each galaxy, there are perhaps 100 billion stars. So if we're talking about big data, the universe is certainly a place where we encounter big data. Now, how do we use these Cepheid variables to measure distances? This was earlier work by Henrietta Swan Leavitt about a century ago at the Harvard College Observatories. And Leavitt discovered this relationship between how fast these Cepheid variables are changing in their brightness and their brightness, the so-called period luminosity relation. And if you can measure, discover these stars in nearby galaxies, which is what Edwin Hubble did and which we continue to do to this day, about 1 in 1,000 stars that we measure turns out to have this property, are Cepheid variables. And we can use this relationship between brightness and the period of the star, and making use of the inverse square law of light, determine the distance to the galaxy in question. And so this is the Leavitt law, as we refer to it today. This is luminosity increasing here, brighter Cepheids and longer period Cepheids. And we can make these measurements in nearby galaxies and determine the distance to the galaxy. We then calibrate this. We use this distance ladder, as it were, making measurements to galaxies in the nearby universe where we can anchor them with geometric measurements and on out to farther and farther distances. And so in the nearby universe, we can determine distances using geometry. And in fact, in our own Milky Way, we can make use of parallax measurements, the Earth's motion about the sun, and make accurate geometric determinations of the distances to nearby stars, including the Cepheid variables and another type of red giant branch star, which I'll talk to you about in a moment. And then we can use the Hubble Space Telescope, go out, find these Cepheid variables and red giant branch stars that are located in the halos of these galaxies, and then use type 1a supernovae, explosions of stars that can be seen essentially halfway out to the distance of the visible universe, and measure the expansion rate of the universe. And this is what we did with the key project that Tamara mentioned. This is showing on the left here Hubble's original diagram where he discovered the expansion. And if we look today at these measurements that Hubble made, they would fit into the first tick mark of this plot. This is this plot of velocity as a function of distance. And this is the Hubble relation that we measured as part of the key project. And Charlie showed a version of this diagram. What has emerged is our picture of a Big Bang universe. We don't see, we have an inflationary period in the first fraction of a second in the early universe. We measure the background radiation and fluctuations in the background radiation about 380,000 years after the Big Bang. And then today in the nearby universe, we can measure the distances to galaxies. Galaxies have emerged from these quantum fluctuations that give rise to the galaxies and large-scale structure that we see today. Now, as I mentioned, most of the matter in the universe we have discovered is dark. It is not emitting radiation. We have many ways of determining that there is matter that we do not see, that it's interacting with the luminous matter via gravity. We see that in the motions of stars about galaxies. They have larger velocities than they would have if there were no dark matter around, if there weren't additional matter. Here is showing what you would expect from the luminous matter that we see in galaxies, but in fact the stars are moving much faster. And that holds also in the motions of galaxies within galaxy clusters. They're moving faster than they would do without the gravitational binding effects of additional matter. X-ray gas, very hot gas in galaxy clusters that would have evaporated long ago if there had not been additional matter to keep it bound to the galaxy cluster. And a prediction by Einstein that there'd be bending of light due to the presence of matter. We see this gravitational lensing, these beautiful arcs as light comes from a background source through a massive object like a galaxy cluster. So the evidence for this dark matter is quite overwhelming at this point. There are many independent ways of measuring the presence of this matter. I won't go let this run for too long, but there are now simulations that include the presence of dark matter and that fit accurately the distribution of matter that we see. What is the dark matter? We don't yet know. There are experiments that are going on, for example, the ATLAS detector at CERN looking for particles that could be the dark matter particles that were created during the Big Bang. Underground laboratories around the world looking for the interaction, very weak interaction of perhaps dark matter particles, and observations, for example, with the Fermi satellite looking for signatures of dark matter particles that could explain this dark matter. Now, as I mentioned, about 70% of the overall composition of the universe appears to be, it's the dominant energy plus mass component of the universe. We're only appearing to see the tip of the iceberg. Most of the matter energy in the universe is in this form, this repulsive gravity form that is causing the universe to accelerate. And I'm realizing with Zoom, if I'm mute, you probably can't hear me, but the objects that were first used that allowed us to infer the presence of this acceleration or dark energy was the explosion that comes from matter coming onto a white dwarf, very dense object in the universe, and which we can see to great distances. They're very luminous, these supernovae, and we can find these explosions in galaxies. Is one shown here. It's a very easy measurement to make. You just look for the arrow in the image. Of course, these occur about once a century in a galaxy. They're actually quite rare, especially as we make these measurements and try and calibrate them in the nearby universe. So the universe is accelerating, and the overall contribution of matter that is in the stars and planets and us, biological matter, turns out to be a very small fraction of the overall mass energy density in the universe. Most of the matter in the universe is in fact in this dark component, and most of the overall budget is in this form of dark energy. And what we've found recently, so that's become what we term the standard model in cosmology. A dynamic universe expanding. Most of the matter in the universe is dark. The total matter content is about 30% of the total, and the energy content due to this dark energy component is about 2/3 of the overall total. And that model has stood the test of time for about 20 years now. but there is some evidence that there may be cracks that are appearing in the standard model, and maybe something that we're missing in our current understanding of the early universe. And this problem people have been referring to as a tension in the Hubble constant. And what it refers to is that measurements that come from fluctuations in the background temperature and polarization of the cosmic microwave background. If you fit this standard model to the fluctuations and the spectrum of fluctuations from the early universe, you can then infer what the expansion rate or the Hubble constant would be today. And if you do that, you end up with a value of the Hubble constant of about 67. The most recent observations using these Cepheid variables yields a value of the Hubble constant of about 74. And of course, what it depends, this tension depends on how well these measurements have been made. And the history of making measurements of the Hubble constant, these are difficult measurements to make. We're trying to achieve accuracies for objects that are millions, if not tens of millions of light years away from us, and then to try and compare what we're inferring in the early universe with what we measure today. And some groups have now concluded that this is a 5 sigma tension, which in the world of particle physics, for example, 5 sigma would be without any kind of question. You have determined that this is a result that's going to stand with time. Now, so this is from the microwave background point of view. You measure the temperature across the microwave sky, fluctuations in that. This is the angular power spectrum as a function of scale here. So this is decreasing size on the x-axis and the power and the fluctuations here. And you can see these beautiful curves here. The points are the data, and the line here is fit to the standard cosmological model that I've been describing. And you can't even see anymore where the curve is relative to the data. It's an exquisite fit. And if you take this standard cosmological model at face value, then you would say you have determined a measurement of the Hubble constant to very high accuracy and precision, less than 1%, if the standard model is correct. So again, we turn to the Hubble Space Telescope, and the question for me is, could there be uncertainties in the Cepheid calibration that would prevent us from measuring the Hubble constant to the accuracy that perhaps now is being concluded? So this is a comparison, recent comparison of the Hubble constant as a function of time. This is our key project value from 2001. We measured the Hubble constant then to an accuracy of 10%. The error bar looks large now, but when we started, the uncertainty in the Hubble constant was a factor of 2 at that point. And in blue here is shown the measurements of Cepheids in the intervening time. And the black are showing the measurements from the microwave background. And the error bars in both cases, a function of time, have been dropping quite considerably. And depending on the uncertainties that you quote, the uncertainty has been estimated as anywhere between 3 and 5 sigma. The error bars are not overlapping, and that's what's given rise to this tension. And the question, is there something about the universe that we don't yet understand, something missing from what we now call the standard cosmological model? So that's what motivated us to try a different method and to use stars that are evolved stars. These are stars not unlike our own sun. Our sun will become a red giant branch star after it burns the helium and the hydrogen in its core. As it's burning hydrogen into helium, exhausts that. Star climbs what's known as the red giant branch. At that point, it has a core that it's degenerate. It's supported by degeneracy pressure and a helium core, and it's burning the hydrogen now in a shell about that core. And the temperature is increasing as it's burning this hydrogen in this shell, and it reaches a point where the temperature is high enough to break the degeneracy in the core, and the star undergoes what is known as a helium flash. it breaks the degeneracy, the star becomes fainter. And what that means in an observational sense is that these stars disappear from the so-called Hertzsprung-Russell diagram. They no longer are as bright as they have been on the giant branch. And so we can use this property, we can go out and survey stars in the halos of galaxies, which we've done with the Hubble Space Telescope. So these are the fields shown in these white squares here. And it looks like there are no stars here, but the contrast, we're looking at the bright centers of galaxies shown here. That's the beautiful part of it, but that's our noise. We avoid the central parts of galaxies and measure stars out in the halo where there are thousands of these red giant branch stars, and we can statistically measure the position, the luminosity at which these stars undergo the core helium flash. And this is just an example of a galaxy, just a 30 million light years or so. And we use the Hubble Space Telescope to identify these stars shown here in the circles. These are these stars at the tip of the red giant branch. So it's a very simple measurement to make. I won't go into the details. For Cepheids, it's actually a lot more complicated to make these measurements because the Cepheids are located in the disk. So the accuracy with which we can measure the luminosities of Cepheids is substantially lower than the measurements we can make for the tip of the red giant branch. So then we can do what has been done historically, compare the distances with the velocities of these both nearby Cepheids and the red giant branch stars. And now using the type 1a supernovae, that we can extend to much greater distances and velocities. And interestingly, we had thought that when we made these measurements, we would be able to discriminate between the results for the Cepheids and the cosmic microwave background. And we landed essentially in the middle. This is a result that we published last summer. Since that time, we've made additional measurements and quite independently of the ones that we published last summer. And we have confirmed this value. In fact, the measurements are coming in at almost identically the same value of the Hubble constant, which is 69.5 or so. And so this error bar is shrinking, and it does overlap. It agrees actually quite well with the recent microwave background observations. And so it actually is raising the question, is this tension real? Or is there something systematically an issue with the Cepheid variable stars? And this is a comparison of recent measurements of the Hubble constant using a number of different techniques. So here are the cosmic microwave background observations. So again, inferring the Hubble constant, if you assume this standard cosmological model, the Planck satellite gets a value of about 67. If you make measurements of the matter density fluctuations in the universe, then and you have to tie those observations then to the early universe. You have to have an absolute scale, and these measurements, all measurements, the supernovae also give you a relative scale. So you have to have some method to give you an absolute scale. So nearby universe, we use geometric parallaxes and other techniques to calibrate Cepheids and tie into supernovae. In this case, the measurements are calibrated using the sound horizon measurements that come from the Planck satellite. So those techniques give a lower value. This is our result from the tip of the red giant branch. And you can see that it agrees reasonably well with the Planck measurements given the uncertainties. And then there are other measurements using properties of gravitational lenses. And this is a recent measurement from this group. They originally had a smaller error bar. In fact, new analysis gives a much lower value of the Hubble constant with a larger uncertainty. And so really the discrepancy comes between the tip of the red giant branch and the Cepheids. That's where the tension is coming. And I think I just mentioned that there is this opportunity to use what are referred to as sirens, or gravitational wave neutron star binaries that are spiraling in and provide an opportunity to measure the Hubble constant quite independently of the nearby universe and Cepheids and the tip of the red giant branch. Unfortunately, those are rare objects. There's only one so far, so it gives a value of 70 with this very large error bar. And we hope in future that technique is going to yield a means of essentially a tiebreaker. I just want to end by saying that there's, in my view, an enormous opportunity to increase the precision and the accuracy of these measurements. One from the Gaia satellite, parallax satellites, and ESA satellite, measuring the parallaxes of stars in the Milky Way. And this, so the expectation is that a new release of Gaia data in December of this year, which will give accurate parallaxes both for the Cepheids and for the tip of the red giant branch, and another technique that we're now developing, and help to, these will be parallaxes that are more accurate. They're at the sub% level, which using those words together in the same sentence for cosmology has never been possible before. And that is likely to shed light on where some of this discrepancy is arising. We're currently observing additional galaxies with the Hubble Space Telescope to increase our sample for the red giant branch and improve the statistical uncertainties in our measurement. And then a year or so from now, we expect the launch of the James Webb Space Telescope. The red giant branch stars that I've been describing are red, and the James Webb Space Telescope is sensitive to infrared radiation, so we'll be able to extend these measurements out to larger volume and again improve the accuracy with which we can make these measurements. So I'm going to stop here and I'll leave the floor open for questions. Thanks very much.
Thank you. Virtual applause. It was a beautiful talk, and you kept beautifully to time, so thank you for that. Let me start with the first question, which is that on the difference between the tip of the red giant branch and the Cepheids, is there an a priori reason to be more or less suspicious of one than the other as a standard candle?
Yeah, so having worked in both, it's a part of what keeps you awake at night are the unknown systematics that could be affecting your measurement. And when we did the Hubble Key Project, the aim of the Key Project was to make the measurements in a number of different ways. And each method will have its own set of systematics. And you do the best that you can to test for systematics, to minimize systematics. But if you're using only one technique, you'll never get to the bottom. You'll never understand what the limit is of the systematics that you just may not be accounting for. And so you may have seen in the plot that I showed from the Key Project, we had 5 independent methods, secondary distance indicators. And in the end, combining those results gave us, I think, a robust measure of the overall systematics. And we also used the tip of the red giant branch and other variable stars, Aurelian stars, to test the Cepheids at that point. And at the 10% level, we did, I think, and the result has stood the test of time, allow for the overall uncertainties. Where we are now, and as we're trying to decrease the errors, the numbers of galaxies that we need and the extraordinary precision that we need, what we saw in the Key Project was the factor of 2 when we were able to remove that, and then 10 or 15% effects that hadn't been known before cropped up. They became the dominant systematic, and I think that's where we are now, and why I wanted to pursue the red giant branch method. So they're very different. The systematics are different again. What I like about the tip of the red giant branch is that we're observing out in the halos now, where, as I showed you, these stars are isolated. So getting accurate photometry of them is very simple. You don't have to worry about the crowding and overlapping of images that we have to worry about with the Cepheids. So when we're observing Cepheids, because Cepheids are young, we find them in the regions where they were formed. They haven't been able to migrate very far. And so there's a lot of gas and dust, and it's the background of the galaxy itself. They're superimposed on the background. And so we need to use techniques that allow us to extract these individual stars from overlapping images of other stars in the disk. And I think we can do that well with the Hubble Space Telescope out to a certain distance. But once we've exceeded that distance, the ability, there could be a star behind our Cepheid. And in fact, so what we have done with the Cepheids is move as far as we can to the red end of the spectrum. And there are a number of reasons for doing that. The amplitudes of the Cepheids are smaller, and the reddening by dust is lower in the infrared. And so you'd like to move as far to the red as you can. The difficulty is, as you do that, the red giants that I've just been describing in the disk, and in fact, a younger population that we don't see in the halo, population of so-called asymptotic giant branch stars in the disk, start to crowd and blend with your Cepheids. And so I think that's the one that particularly worries me. We also have to worry about whether different abundances in the Cepheids, in the atmospheres of these stars, how that's affecting the luminosities of the Cepheids that we observe. And that's a difficult measurement. We've been trying to study that for decades, and there's no agreement amongst the various groups about how big an effect that it is. With the tip of the red giant branch stars, that's a very easy measurement to make, and we can make it directly for them. So at the current time, what I would say is that the potential for systematic errors in the Cepheid distance scale are larger than for the red giant branch stars. And particularly because, as I mentioned, we now have two independent ways of calibrating the tip of the red giant branch. And so beyond what we did last summer. And they're coming in with, the agreement is excellent with the different methods that we've used. So we've used the Galaxy NGC 4258, which has a black hole in its center, and for which you can measure megamasers that are orbiting the black hole. So it's another geometric technique. And we calibrate using that, and it agrees with what we did last summer. We've also used stars in our Milky Way galaxy and globular clusters to calibrate them. And they're giving a consistent result. With the Cepheids, when you use those three different calibrations, you get actually quite a large spread. And so the calibrators, the anchors, are not agreeing. So for those various reasons, at the moment, I think that there's more uncertainty in the Cepheid distance scale. And I say that having worked on both of them.
Yeah, you seem like the right person to ask. Thanks. There was a question from Charles Lineweaver.
You're still awake.
I am, thank you. Anyway, Wendy, thank you for your clear and measured words. I'm worried about this tension, as many people are, and I'm concerned about a specific selection effect, and that is when occasionally I run across papers that say, oh, the large scale flows in the universe are larger than we think. And I'm wondering if that is an issue, if you look at how homogeneous are the observations you're making in the sky. Can the Hubble constant, at least locally, be a function of where you're looking, and how homogeneously have you looked for that selection effect in particularly when I guess your nearby observations of the Cepheids, which would be more susceptible to large scale flows?
Yeah, so let me say a couple of things. So first of all, we can place very tight constraints now on the inhomogeneity based on the supernova observations. So when we started the KEY project, a few decades ago, and the tension then was between a Hubble constant of 50 and 80, or even 50 and 100, that was a very large effect. And people really did worry that that was part of the issue. Now, when we look at the type 1a supernovae and look at the Hubble diagram and the scatter about the Hubble diagram, that effect is really constrained now to be less than 1% effect. And in fact, if the differences were that large, you would see the effects in the microwave background. We just don't see very large voids. And so, my guess is it's contributing a little bit of noise at the percent level, but what people are asking now is for percent level accuracy. And so that is important at that level, but it doesn't explain the whole tension. The difference between 67 and 74, 7 kilometers per second per megaparsec. There's nothing that people have done simulations of these simulations of motions in the universe, and these just large inhomogeneities don't show up. With respect to the question of the nearby universe, we don't use those, all we use are the distances. We don't care about the velocities. We're just using them as an anchor for the distance scale. So if you recall the plot that I showed, there is much more scatter in the local Hubble diagram, and that's a result of gravitational interactions, these peculiar velocities that affect the nearby objects. In a relative sense, nearby objects affect them more than the distant objects, but we don't care about the velocities. We're only using the distances that we measure. So that's not an issue at all.
So if I've understood you correctly, if you made a full sky map and gave it colors according to which values of the Hubble constant you get as a function of position in the sky, that the differences would be much smaller than the error bars that you're reporting on any of these values?
Correct.
That's an unambiguous answer.
There is, you see the scatter, but it is just not large enough to account for this 7 kilometers per second per megaparsec difference. It's
okay. All right, thank you.
I see a raised hand from Gijs Verdoes-Klein. Gijs, please go ahead.
Yes, thank you very much for a wonderful talk. As you very much know, much better than I, and Koen knows as well, there are also tensions between big lensing tomography and the Planck in different senses, but also on the cosmological standard model. And so for me, it's amazingly impressive that now you have the red giant branch stars and the Cepheids, a way to build up Rosetta stones that you can go to certain galaxies and measure in both ways, what their distance is, and thereby try to distinguish, are we indeed going towards this Planck model, or are these weak lensing tomographies and the Cepheids pointing more to another direction? And so my question is an observational one. How much build-up will there be in the coming years of building up these Rosetta stones to weed out indeed that Cepheids maybe have a systematic issue?
So let me just pick up on that. So I'm not exactly sure what you're asking about the Cepheids. So can you just, what exactly?
My question is, you can build up samples of measuring distance to galaxies, both using the red giant branch stars plus Cepheids for the same galaxy, and thereby, weed out as if it were a Rosetta Stone, which one is right and which one is wrong.
Yes.
And so my question is, how much potential is there in the coming years when you think of JWST, but perhaps also ELT, to actually enlarge that set of Rosetta Stones?
Yeah, so I think this opportunity now, and we don't have it for other techniques, to measure the distances directly to the same galaxies. And so at the moment, the Cepheid distance scale is based on measuring Hubble Space Telescope distances to a sample of 19 galaxies. That's what's been published so far. And those galaxies all have had type 1a supernovae in them. It's a small sample. And the reason for the small sample is because type 1a supernovae are rare. And so what we can measure in our local volume, there may be one supernova every 2 to 3 years that is close enough. So it's within the accessibility of Hubble to measure an accurate Cepheid distance or TRGB distance. We have 18 in the TRGB sample. For various reasons, the overlap of those two samples, there are 10 galaxies for which we have both tip of the red giant branch and Cepheid distances. Now, for the tip of the red giant branch, we are not confined to the disks of spirals the way the Cepheids are, because Cepheids are young. We only find them in spiral or irregular galaxies. And we can measure the giant branch stars in elliptical galaxies or inclined spirals where you can't measure the Cepheids just because, again, the density of stars is too high in the highly inclined spirals. So it's going to take a long time to build up the sample. I will say there are more Hubble Space Telescope observations looking for Cepheids and for which we're making TRGB measurements. it isn't clear yet how far Hubble can be used to make these measurements. And that, I'm saying, for the reason that I described before, the farther out we go in distance, the worse our resolution, and the crowding and blending issue that I described becomes more acute. And so it's not simply a matter of building up the sample and statistically beating down the statistical uncertainty. It's taking into account the systematics, and there may be a systematic effect of these crowding and blending effects. And my worry is that as you go in the inner parts of a galaxy, there's more dust, there's more crowding, and the metallicity of the stars, the abundance in the atmospheres, is increasing. And all of those effects are, there's an interplay between those effects. So I think we're going to be able to take the tip of the red giant branch method out farther with the James Webb Space Telescope. So these stars are matched in terms of the sensitivity of the JWST. And unfortunately for the Cepheids are relatively blue stars, and their amplitudes are largest in the blue part of the spectrum. And so when we find the Cepheids, what we devised as part of the key project was a way of finding the Cepheids in the blue part of the spectrum and then following them up at redder wavelengths. And we won't be able to do that with James Webb. So it's a long answer to say this is actually a tough problem. There aren't that many. We're going to have to wait many years for the supernovae to go off, and there aren't that many objects in the nearby universe for which we can make these measurements. The JWST, though, will allow us to increase the volume by roughly a factor of 10. And so we will be able to extend the TRGB method much farther with JWST. So there is a lot of promise there.
Thank you, and thank you, Wendy. I think in view of time, we have to stop the discussion here. There's some more questions, but I'm afraid we can't get to them. So